Okay, so we are recording. So by popular demand, we're going to start with a Doppler effect question. And this isn't a textbook question. This is one that I made. And it's quite thorough. It's a heavy question. You won't have something this long on your test, but it does cover a lot of different types of concepts and aspects of Doppler effect that you might need to know. So we can go through and do most of this question anyway. Excuse me. Okay. So we're going to do Doppler effect with a cat, which is not super realistic, but I have cats running crazy in the background behind me here because I haven't fed them yet and they're mad, so I thought it would be appropriate. So let's start just with the first part of this question here. Okay, they're saying that you have a cat, or maybe it's my cat you're listening to, and the cat is meowing at a frequency of 4,000 hertz. Assuming that sound is moving at a speed of 343 meters per second, which is pretty typical. That's the speed of sound for, I want to say 20 degrees or something, but I'd have to pull out the exact formula to tell you for sure. But it's a pretty typical speed of sound. And so my question for you is, what frequency do you hear if, and the first part is if you're running towards the cat at a speed of 5 meters per second and the cat is sitting still. So we have for determining frequencies, use a change in frequency because of a Doppler shift. We have two very similar equations that we can use, and they have the form something like this. The frequency f is equal to f naught, or f sub 0, which is the frequency that you would observe if you weren't moving, divided by 1 plus or minus, depending on the direction you're moving, and we'll figure that out in a second, Vs over V. And I find this confusing, this subscript, I just selected everything. The subscript Vs, I always think, is it the speed of the source or the speed of the sound? And what this means, Vs is the speed of the source. So in this case, that would be the speed, well, we'll get into that. It's the speed of the source, what's making the sound relative to you. And the just V is the speed of sound in the current medium. And so this is the formula we'll use. And pretty much all we have to figure out is this Vs, should it be positive or negative? And well, and I guess it gives us the speed that you're running towards your cat at 5 meters per second. So it's basically figuring out what the sign of this should be. And then just plug in the information and find the frequency. So what we have is that the actual frequency, or the frequency that you would observe if you weren't running towards your cat, is 4,000 hertz. And we're going to divide that by 1 plus or minus. We still haven't figured that out yet. The speed of the cat, which is 5 meters per second, divided by the speed of sound, which is 343 meters per second. Now, I said the speed of the cat is 5 meters per second. Technically, in the question, I said you're running at 5 meters per second, but if you're going towards the cat at 5 meters per second, that would have the same effect as the cat running towards you at 5 meters per second. So now we just have to figure out what the sign should be. And you could memorize, plus or minus, depending on whether you're getting closer to the source or further from the source. I like to draw a little picture because, I don't know, I find that memorizing the signs gets confusing sometimes. So here you are running towards the cat. There's the cat. And the cat is meowing. And there's the sound waves that the cat is meowing and sending towards you. And now, if you're going towards the cat, these sound waves are going to get squished together. So when you perceive them, you'll actually see them something more like this, if you'll pardon my sketchy sketch, my drawing. Anyway, they'll get closer together. Closer together means that the frequency is higher because you would have more cycles or more waves in a shorter distance. So the frequency that you should observe should be higher than F naught. So based just kind of on this reasoning, you can say that F should be bigger than F naught. And so for the frequency that you observe to be bigger, the denominator of the right-hand side of this equation, the denominator should be smaller, so that overall the right-hand side gets bigger. All to say is that you would have 4,000 hertz divided by 1, and we're going to make this minus, well, I'll just write it as 5 over 343. And so we chose to make this a negative sign because we need for the frequency that you observe, it should be bigger than the actual frequency. And so for F to be bigger, that means it's equal to this fraction, and so the denominator should be smaller, and we made that a negative sign in the denominator. Also, in your textbook, in equation, actually, I'm not sure what the equation number is, because my book is a different, I don't know, it's just a different. Oh, hello? Can you hear me?
Yep.
Okay, thank you. Anyway, in your textbook, when it gives the equation for Doppler shift, it says that the Doppler effect for an approaching source has the minus sign in the denominator. So if you prefer to think about it that way, that all checks out and does exactly what it's supposed to. So putting this in your calculator, assuming I don't mess up, which I'm kind of known for by now, I'm getting a frequency of just over 4,000 hertz. I'm getting about 4,059 hertz. And so that's how fast, that's the frequency that you hear the cats meow at. Okay, now let's make this a little bit more complicated. This time, let's give myself some space. This time you're still running towards the cat, but now the cat is running away from you as well. So as a picture, here you are. I don't know how to run stick figures drawing, so it kind of looks like a spider. You're running towards the cat at 5 meters per second, but the cat is going away from you. There's the cat is running away from you at 8 meters per second. So overall, you're getting closer to the cat, but the cat is getting further, is going away from you faster. So overall, the cat is going away from you, and the relative speed between you, or how much you would measure the cat is traveling away from you, would be at 3 meters per second. So that's because the cat is running at 8 meters per second, but you're going 5 meters per second, like trying to catch up. So overall, relative to you, the speed of the cat, or of the source, is 3 meters per second, and this is relative to you. So putting that into our same frequency, same frequency, same formula for the frequency. We'll have the frequency that you hear equal to f naught over 1. This will be plus this time because overall the cat is running away from you. Plus vs over v. So plugging some numbers in, the cat is still meowing at 4,000 hertz, which is pretty screechy. I don't know if you have an idea of where that sound is, but it's pretty high pitched, pretty annoying, just like a cat. So in this case, since the cat is I made a mistake in my calculator. Since the cat is like moving relative to you at a it's at a slower speed, so the frequency that you observe won't be as different from the actual frequency, but also since overall the cat is moving away from you, the frequency should decrease. And so again, that's why we have that plus sign in the denominator. And so I'm getting a frequency here of about 3,965 hertz. Still obnoxious, but a little bit lower than before. Before we move on to the next one, I just want to check in. Do you have any questions, or are things going good with you? Let me know in the chat. Okay. Okay, question in the chat. There's another equation that uses 1 plus, okay, I'm going to write out the equation that you sent in the chat here. Okay, so you said that the equation you have, correct me if I'm interpreting this wrong, but you have it as f is equal to f naught times 1 plus v observer divided by v. So that's
just the v observers divided by v.
Oh, not the 1 plus. Okay, thank you for clarifying that. Okay, so this equation, what this equation is doing is it's kind of, well, it's doing two things. I guess the main part is that it's changing the speed of the source into a speed of the observer. And so it's playing around with the signs in that way, because I guess this is awkward because you haven't really done much relativity yet. But pretty much however fast you're moving towards the cat, you could say that the cat is moving away from you at the same speed, depending on whose point of view you're looking from. But the directions that you're moving at would look opposite to each other. So the cat would see me going forwards towards the cat, so the cat sees me going forwards. But if I'm just standing here and it's the cat moving towards me, then I see the cat going to the left. So those speeds have opposite signs. So in this equation that I've written in blue that I can't see because there's a real cat in my way now, there we go. In this equation that I've written in blue, they've switched out the speed of the source with the speed of the observer, and then they've just done some algebra to write it in a different way. If you're getting a slightly different answer, that would just have to do with the way that this blue equation is rearranged differently from the pink one I have written at the top left. It's just rounding your answer a little bit differently. So it doesn't matter which formula you use. They both work. And if you feel more comfortable with an individual formula for each case, absolutely go with the blue one. If you would rather just use this, I guess, this initial or like the original equation we were looking at and just apply it to different situations, that works as well. But to answer your question, it does not matter which one you use. So it seems like everyone is doing pretty good with these questions with the relative velocities and seeing the Doppler shift because of that. So I have two more examples of different ways that you and your cat can move. These seem redundant. If you're having no problems with what we've done so far, let's go on to these last couple of questions, which are a bit more interesting. Oh, one more question. If you can answer in the chat for me, did you talk about sonic booms in this class? I don't remember seeing them in the textbook, and but I'm not sure if Amy mentioned them in the lecture or not. Okay, so you've seen these a little bit. Okay, well, this is a fairly straightforward example of sonic boom. So if you've seen it a bit, if you've talked about it a little bit, we can go through it. So in this next question, now we're saying that you are not moving. So you're just standing there, just hanging out, and your cat is running. And so my question is, how fast and in what direction would the cat have to run for you to perceive a sonic boom? And so a sonic boom, or I don't know, there's other words for it, but that means that the frequency you hear is infinite, or like all of the sound waves hit you at once. So not only do they get compressed, they are, so do a picture to go with this. The cat's sound waves, that's what they would be like normally if the cat was running towards you. Can I click these? I can't. The cat's running towards you, these would get compressed. If the cat's running away from you, they'd be lengthened. How fast would the cat have to go for these to get compressed so much that they all overlap? Okay, I'm seeing in the chat that the cat would have to have a speed. So Vs for the speed of the source, which is the cat, has to be 343 meters per second. Absolutely. Another way of saying this is that the speed of the cat, of the source, is equal to the speed of sound. What direction would the cat have to move in? Would the cat have to move towards you, away from you? Towards you, absolutely. So the cat is running towards you at the same speed as the sound that the cat is making. So the speed, I guess a way of thinking about it is that the speed of the sound is the same as the speed of the cat. So the sound waves don't have time to go away from the cat. And so by the time the cat gets to you, all of the sound that the cat has made in that time is hitting you all at once. And so in that case, the frequency is infinite because there's no space between meows or anything. You just hear the meows all at once. So we say the frequency is infinite, and it makes a sonic boom. And that's like when jets go really fast and break windows and things like that. That's what's happening there, is you get this shock wave from the sound waves in the air, all like this really high intensity, super high energy sound wave all traveling through the air, and all of this sound hits the glass window all at once and makes it break because of the force it's hitting it with. Yes, thank you for putting that in a mathematical way. I'll write that out so everyone can see. So in the chat, I'm saying that for the frequency you observe to be infinite, this means that in your formula, F0 over 1 minus Vs over V. Absolutely. So if you plug in V for Vs, so we said here that they're equal, you just have V over V, which would be the frequency F0 divided by 1 minus 1, which is F0 divided by 0, and that's what makes it infinite. So there's the mathematical reasoning for it. And if you remember from calculus looking at vertical asymptotes and things like that, that's what this is creating here. The frequency just goes up and up and up and up and up. And the frequency becomes, or I guess approaches infinity as the speed approaches, like the speed of the source approaches the speed of sound. I don't think you'll have to go into this much math detail on a test or anything, but that's the idea behind it. Ooh, okay, interesting question in the chat. Someone asked, what happened when the speed of the source is faster than the speed of sound? So V of the source is faster than just V, which is the speed of sound. That is a really interesting question. Let's look at the math to tackle that one. And that's what I do when I get lost with physics. I look at math and try to make that make sense. So if you have that the speed of sound is bigger than, or sorry, the speed of the source is bigger than the speed of sound, you'll have F0 divided by 1 minus Vs over V. But Vs over V is going to be bigger than 1, right? And so if this thing is greater than 1, that means your denominator is going to be negative. You'll have 1 minus something that's bigger than 1. And so what this means is that the frequency that you observe is going to be negative. It's going to be less than 0. And so a negative frequency is weird. It's weird to picture. It's weird to kind of visualize. I think you put it in a pretty good way in the chat. You said waves imploding behind the cat. Kind of, yeah. So what would happen is that the cat would get to you before the sound that the cat is making gets to you. And so that negative frequency, I guess you could think of the negative frequency as being kind of a reverse of cause and effect. So normally you would hear a cat approaching before the cat actually gets to you, unless the cat is waking you up in the middle of the night, which may or may not be a true story. But you would hear the cat before the cat actually gets to you with a positive frequency according to the Doppler shift. If there's a negative frequency, that means that the cat gets to you before the sound that it already made gets to you. This isn't something that you're going to be tested on, and that I don't think that's going to be asked. It's kind of an interesting thing to think about, though. And Avienda the kitten agrees. All right. Okay, let's do this last question quick because it's just solving for a different thing, and then we'll move on to a different type of question, something other than Doppler shift. So now, excuse me. Okay, so now the cat is meowing at a different frequency. And I don't tell you what the frequency is, but just some frequency. And let's call it frequency of cat. Is the frequency the cat is meowing at. And that is the frequency you would measure if you're not moving relative to the cat. F cat, there we go. So my question for you is that if that's the frequency that the cat is meowing at, and you stay still, you're not moving, at what speed would the cat have to move? How fast would the cat have to run if you were to hear a frequency that is half of the actual frequency that the cat is making? So F cat, that's what the cat is meowing. And the frequency that you hear, and we'll just call it F, is equal to a half the frequency of the cat. So in the chat, can you tell me what direction would the cat have to move in for you to hear a lower frequency? And while you're typing, I'll draw a picture. This is a terrifying cat. Yes, absolutely. Good job, everyone. The cat has to run away from you, which I guess I kind of gave it away with my drawing. If you can tell that that's a cat in the first place, which I won't be offended if you can't. Yes, the cat is running away from you because that will elongate the wave, which decreases the frequency. Okay, I see some calculations. Nice, let's go through it. So here's our formula. Frequency you observe is the frequency of the cat divided by 1, and this will be plus V cat over V sound, I guess. I can say, well, the frequency that you observe is going to be half the frequency of the cat. And I'm just writing the rest of this in, I guess. And so now we can pretty much just take this equation and solve it for the speed of the cat. We can cancel out the frequencies of the cats on both sides. And eliminate that from the left side and from the right side. And so we have 1/2 is equal to, now it's just 1 divided by 1 plus V cat over V of the sound. And now we just get to play around with the algebra of it to isolate for V cat. So I'm going to start by doing the reciprocal of both sides, or flipping both sides. So on the left-hand side, I'll have 2 is equal to, and then 1 plus V cat over V on the right-hand side here. So 1 is equal to V cat over V. And so the speed of the cat would have to be the same as the speed of the sound itself. And so we said that the speed of the sound was 343 meters per second in this question. So the speed of the cat is also 343 meters per second, and that's away from you. Okay, how are we feeling about Doppler shift? Can you tell me in the chat? Okay, all good all around. Let's see, what do we have next? Okay, let's do a sound intensity question. These types of questions usually aren't too hard. They're just some formulas and some things to work out. So this is a textbook question. This is question 40 at the end of the chapter. And so for this question, we have that the sound intensity level, which I think is represented by the letter capital I here. But I'm going to double check because I get the letters mixed up a lot.
I think it's beta.
I think you're right. Thank you. It is beta, and I is just the intensity. So for my own benefit, as much as fears, I'm going to write this out right away. So I is just the intensity. And the intensity is a power per unit area, or it's an energy per time per area. And so I'm just going to write that in so I don't forget again. Energy per time per area. That's the capital I. The intensity level is just like a scaling system, or just, I don't know, a way that some physicists once upon a time decided would be a better way of comparing sound intensities. So beta is the intensity level. And the intensity level is defined with this equation here. Beta is equal to 10 decibels, which is just providing beta with a unit, multiplied by log base 10 of the intensity divided by I naught. And I naught is a constant. It's just like a reference value. And so that's a constant that you'll always just plug into the formula as, I'll write it out here. I naught is equal to 10 to the minus 12 watts per meter squared. So so this I naught is just like your reference value, and it's also a way to make the units cancel out inside the logarithm. So whatever intensity you have, and you plug it into the formula, the way they've built the formula and the way that they have defined the intensity level, when you plug in your value for I naught, it'll handle all the units and make sure that everything works out nicely. So there is the formula for beta. Now, this question is saying that the sound intensity level, sound intensity level 5 meters. I'm not sure why there's a 5 meters there. Oh, at a distance of 5 meters, I guess. From a large power saw is 100 decibels. So at what distance will it be 80 decibels? So there's one more bit of information, or one more relation we have to introduce here, because so far we haven't really talked about a distance yet. We've just really defined the intensity and intensity level. But so here's our intensity level. Actually, let me get a different color so I don't lose track of it. We being me. Is the intensity level. I'm also going to define the intensity itself in a more mathematical way. And this is the power per area. The power being the energy per unit time. That part is the power, and then we divide it by area. And with sound, with a sound energy or sound intensity, the sound propagates outward in a sphere. So if you have a speaker that's playing music or whatever, or this saw in this question, the sound waves that it generates kind of radiate outwards in a sphere, just because we happen to live in a three-dimensional world. So the area that we're looking at then is just a sphere with a radius r. And so depending on how far away you are from the source, that would be the radius of the sphere that is propagated outwards, and you could find the intensity that way. All to say, this area that we consider is the area of a sphere. So we can write the intensity as, maybe we can, power divided by the area of a sphere, which is 4 pi r squared. And r is the distance So the distance to the source. Okay. So these are kind of the two main equations that we'll use to tackle this question. And so what it's saying is that if you are 5 meters away from the power saw, the intensity level that you hear is 100 decibels. And so what we can do is use this first bit of information that they've given us, being 5 meters away, and at that distance it's 10 decibels. We can actually use that to find how much power is output from the machine, from the power saw. And the reason that we want to find the power is because that is just a property of the saw. So the power that it's putting out isn't going to depend on how close you are to the machine or anything like that. It's just a property of the saw itself. And so it would be constant no matter what distance we're at. And so we can use that to find the distance for the next part. So taking the two equations we have here, we have the distance. And so we're looking for the power. So I can start by writing I is equal to P over 4 pi r squared. We have r, that's the 5 meters or whatever. But we don't have the intensity itself. So what we can do is plug this into the equation for beta and solve for power that way. So we can write that beta is equal to 10 decibels times log base 10 of the intensity, which is this power over 4 pi r squared. So I'm going to write that in right away. And this is all divided by I naught. And so we can use this equation, this like combination equation that we've come up with so far, to find the power, which means more algebra. Yay. Okay, I just simplified that a little bit. So I guess you can plug your numbers in and then rearrange, or we can rearrange it first and plug your numbers in. I think I'll rearrange first because you all know how reliable I am with a calculator. Not at all. So I like to save that part until last. So I'm going to take beta and divide it by 10 decibels, which leaves log base 10 of the stuff. And so now we can do 10 to the power of both sides to get rid of this logarithm here. So I'll have 10 to the power of beta over 10 decibels is equal to, and so that 10 to the power will cancel out the logarithm on the right-hand side. We'll have P divided by 4 pi r squared I naught. And so now to isolate this and like rearrange it to solve completely for power, we'll just have that power is equal to, well, I guess we'll multiply this denominator over to the left-hand side here. So I'll have 4 pi r squared I of the meeting. Hello. Can you? Hello.
We can hear you now.
You can. Okay. Okay, my internet just kind of kicked me out. Thanks. Okay, so, I guess where I was at, we've got this kind of final equation for power once I've rearranged it for power. And so now I can just plug in the numbers and then shakily type it into the calculator. So R is the distance from between you and the source, which in this question was 5 meters. I naught is that constant 10 to the minus 12 watts per meter squared. This watts being the units of power. So the units will work out here. Times 10. And it said the value of beta in the question, it says that the sound intensity is 100 decibels, so we'll just plug in 100. Okay, I'm going to attempt to put this in my calculator. Let me know how I do. Okay, so I'm getting exactly watts, or if you can say approximately 3.14 watts. Did I do that right? Are you getting the same thing? You're getting 31.4. Uh-oh, what did I do? 4 pi times 25 times 10 to the minus 12 times 10 to the power of 10. You're getting pi as well. Huh. Okay. Yeah, if you were getting 31.4 instead of 3.14, you might have missed a factor of 10 somewhere. Or, I guess, like, divided by 10. Double check that calculation. It looks like we're all getting pi. Okay, so that's the power that the speaker is emitting, and that's constant for, or not the speaker, for the saw. That's constant for the saw. It doesn't matter where you stand, that is always the power that it emits. Well, until you turn it off and it's not making sound anymore. So now what we're looking for is the distance you'd have to be from the saw. So now we know what its power is. We're looking for the distance you'd have to be for the sound intensity to be 80 decibels. And so what we can do for this one is we'll have 80 decibels as our value for beta. Power is going to be the same 3.14 watts. And now we're looking for the value R. So we can, so this equation that we used here, or whatever version of it, we can just solve that for R. So there's our equation that has beta, which we know, power, which we know, and we are looking for R here. Okay, I'm going to do this one a bit differently and plug numbers in as we go and see if that goes any smoother this time. So we want the intensity level to be 80 decibels, which is just, I don't know, easier on the ears. The power we found was, might as well leave it as pi watts so we can cancel out with the pi in the denominator. We'll have 4 pi r squared, which we're looking for, times I naught, which is 10 to the minus 12 watts per meter squared. Pardon my squished and messy writing. Okay. So 80 divided by 10, we have 8 equals log base 10 of the stuff. We can simplify this stuff a bit. This is a 2 here. Sorry, it should be times 10 to the minus 12. Okay, canceling out the logarithm, we can do 10 to the power of both sides. And then it's just solving for r from here. Okay, so I'm getting, this should be, yes, 2,500. I'm getting that for the sound intensity to drop to 80 decibels, you'd have to be a distance of 50 meters away. How'd that question go for everyone else? Any questions about it? Is it going good? Let me know. Okay, so you used, okay, there's another formula you can use to, and it gets the same result. Okay, good. So it seems like this question's going well. It is getting close to 7, but I will do one more question. If you'd like to stick around, I'm going to do question 22, which is a speed of sound type question. So if you think this would be helpful, stick around. If you need to go within the next 2 minutes, don't let me stop you. So this question, let's see. We have a hammer that taps the end of a metal bar at room temperature. So here's our metal bar. It is 4 meters long. And so for this question, it's like the hammer, let's see if I can draw it here. The hammer is hitting it like right on the edge here. Yeah, that's not bad. That looks kind of like a hammer. That just ruined it, but you know what it's meant to be. There's a hammer and it hits the edge here. And so there's sound waves that go through the metal and also sound waves that go through the air. Those are terrible, but that's the idea. And so at the very end here, the very end, we have a microphone. I don't know what microphones look like. We'll say that. And the microphone picks up both sounds. It hears one sound that came through the metal and one sound that went through the air. And it takes 9 milliseconds, or there's like a 9 millisecond delay between them. 9 milliseconds being the value of the time difference. And we can write that as 9 times 10 to the minus 3 seconds. And so this question is saying that so given this information, we also have room temperature, which, correct me if I'm wrong, and I actually do let me know in the chat if I have this wrong, but I'm pretty sure they say room temperature is 25 degrees Celsius, but it might be 20. Let me know in the chat if I have that wrong. In the meantime, though, we're going to use all this information to figure out what is the speed of sound in the metal. And we're saying room temperature is 20 degrees. Cool, thank you. Okay, so what we can start by doing is finding the speed of sound in air. At this temperature, we have a formula for that. I'm gonna have to flip through my textbook here to find it because I don't remember off the top of my head. Or actually, we don't have a formula. We just have a number, a constant. Even better. So instead of using a formula, it says in the textbook, and if you're the type of person who likes to write formula sheets before your test, this might be a helpful thing to add, that it says that at 20 degrees Celsius, the speed of sound in air is equal to 343 meters per second. Just like the cat question. So no calculations needed. That's just a constant, something that you can look up easily. That's the speed that the sound is traveling at. So instead of calling it speed sub sound, I'm going to call it speed sub air. All the speeds that we're looking at are speeds of sound, and we're looking at the speed in the air versus the speed in the metal. So I'm going to distinguish it that way. So if the speed in the air is traveling at 343 meters per second, we know that it has to travel 4 meters, at least 4 meters, to get from the hammer to the microphone. We can figure out how long that took. So V is equal to delta X over delta T, or we can say that delta T is equal to delta X over V. Delta X just being the distance that it has to travel, which in the question says is 4 meters. So the amount of time that it takes for the air wave, or like the sound wave in the air, to go from the hammer to the microphone, that's going to be 4 meters divided by 343 meters per second. And I'm running out of space, but I'm getting a time of about 0.01 seconds. Oh goodness, what did I do? Okay. Okay, so this ends up being about 0.011166 seconds. So that's how long it takes for the air wave to get to the microphone. Now, question for you, and put the answer in the chat. Which sound wave, which sound pulse, I guess they call it in the question, would the mic hear first? The microphone hear the sound traveling in the metal or in the air first? What do you think? Let me know in the chat. Okay, yes, the metal, the sound will travel through the metal faster. And so it will hear the sound coming through the metal first. The explanation is actually a bit more complicated than the density of the materials. It has to do with how the density is distributed throughout different materials. It's a whole thing. It's not super important for this question as to why sound gets to the mic first. Density does have a role in it, so I guess you can think about it that way. But just keep in mind that the speed of sound in different mediums is a bit more complicated than just depending on the density. In the end, though, the speed in the metal will be bigger than the speed in the air. And so that means that the amount of time that it takes for the sound to go along the 4 meters, the amount of time that it takes for the sound wave to go through the metal is going to be less than the time it takes for sound to go through the air. So I'm going to write a little air subscript here on my delta T that we already calculated. So since the wave should take, like the sound wave, should take less time to propagate through the air, or through the metal, less time in the metal because it's going faster in the metal, we can say that the delta T for the metal is equal to delta T for the air minus the difference in time for when they arrived. So writing this as a formula, which is probably easier than trying to picture it with me saying this, we'd have that the time it took for the sound to get to the microphone through the metal is going to be equal to the time it took to going through the air minus just the delta T, which was the difference in time, or like the delay in time for the pulses or the sounds that the microphone heard. And that was the 9 times 10 to the minus 3 seconds. And so we can just plug in the amount of time that we found that it took to go through the air minus the time delay between the two mediums. And that says that the amount of time that it took the sound to go through the metal was, I'm getting about 2.66 or so times 10 to the minus 3 seconds. So that's how long it took for the sound wave to go through the metal. Now to find the speed of sound in the metal, we just have to divide 4 meters by this time that it took to travel the 4 meters. V metal is equal to, I'm just calling it delta X. You can call it like L or D or whatever you want to. And that's just the 4 meters that the sound traveled through the rod, and that gets divided by 2.66 times 10 to the minus 3 seconds that we calculated it took to travel this distance. And so I'm getting about 1,503 meters per second being the speed of sound in the metal. And so that was the last question that I had in mind to do with you. Do you have any last minute questions? Anything else you want to ask about? Just zoom out so you can see everything. We did a lot tonight. Look at us go. Is there anything else you want to ask about before we call it a day? All right, seems like everyone's good. So we'll end that here. Just give me a second, I'll stop the recording.